Okay, so last time we talked about remember we talked about strings and open tubes. We are taking notes. We're going to finish up chapter 26 here. So remember, in our tubes, we had, when we talked about closed and open tubes, things like that, we had our strings and the open end tubes had the same rules. Remember, we had to have an anti-note at the end. But also remember, so it's the length of the string, like the fundamental is twice the length of the string, the wavelength. But always remember that when you talk about tubes, that it extends a little bit beyond the open end, because if I put my hand on top of this, notice it doesn't do anything. Because when I put my hand on here, it does not allow the standing wave to form. Because the length is what we call the effective length. It actually extends beyond the ends of the tube on that. So today we're going to talk about tubes with one open and one closed end. Like that. The rules are a little different here. A node must be at the closed end and an antinode must be at the open end. All open end tubes have an antinode. The closed end has to have a node for the standing wave to form. Now, we could get antinodes at either end, or nodes at either end, it's not going to form a standing wave. In order to get the reflection off the open end, you have to have that antinode. And the fundamental frequency has a wavelength 4 times the effective length of the tube. 4 times. Remember, the other time it was 2 times. Now we're 4 times. And another thing, we only get the odd harmonics. We don't get the even harmonics. So we only get an F3, an F5, an F7. And we need a little more time. All right, so now let's keep in mind. Guys, focus. So, remember, one wave is 2 antinodes. But remember, the first one here that forms up, we have a node and one antinode. So if I start this node and I go to the first antinode, how much of a wavelength is that? That's a quarter. Right? 1, 2, 3, 4. 4 quarters. There, F1. And remember what our definition is. The wavelength is 4 times the length of the tube, which means the length of the tube must be 1/4 the wavelength. 1/4 the wavelength. But remember when we did the other tubes and strings, every time we went up, the other ones, we start with an antinode, and we went up 1 antinode each time, right? We go up antinode, antinode, antinode. Well, here, if I start with half an antinode, the next one should go up another half, right? But if the next one, which would be our F2, if I went up a half, when I go up a half, well, the next half wavelength, that puts what at the end? Node. Now, I could get a wave with a node at the end, but is that going to be a standing wave? No. This is why we don't get even harmonics, because the even harmonics have a node at the open end. Only odd harmonics put an antinode at the end. So again, because we're skipping the even harmonics, every time we always go up by 1 antinode. We're always adding an antinode each time. Because that's where the next one, right? From here to here is basically 1 antinode. That's 1/2 of a wavelength on that. Because that's where the next antinode is going to appear. So the next one would be here. And notice that is 3/4, so that's 3F1. 3/4 of a lambda, 4/3 times the length. F5. Again, we're going to go up another, that's 5, F1. We're going to go up another, add another antinode. Now we have basically 1, 2.5, or 5/4. Fourth is L. So, based on look at the pattern, predict what F7 is going to be. Write down the information for F7. Write down that information for F7. What? You had the right little thing with the pins. You can make big ones. Same idea of a player piano. All right, so F7, how many times F1 is that going to be? 7 times F1. L is going to be what? 7/4 lambda. The wavelength is 4/7 times the length of the tube, which means now we're going to add another antinode. Something like that.
Ooh, I was right.
So we have 3 antinodes and a quarter. Now keep in mind, I don't know if I was as clear about this on the other one as possible. All these are layered on top of one another. Now when you did your experiments and you just got one of these, and you got a nice sine curve, you basically were only getting the fundamental. That's our like tuning fork. But a real musical instrument, if you were playing like a trumpet, you would get this one on top of that one, on top of that one, on top of that one, on top of that one. And then which is why instead of getting a nice sine curve like that, you get these curves that are kind of up, all over the place and up and down like that. And they kind of go all over the place because you've got constructive and destructive interference from all of these waves. Okay, but this is what gives this. But this is why different instruments do sound different. I mean, technically, if a clarinet plays a middle C, and a trumpet plays a middle C, and a saxophone plays a middle C, they're all playing this. In theory, they're all playing the same frequency note. If they're playing a concert where they're all playing, in theory, the same frequency note, do they sound alike? No, because these different harmonics add in to give them kind of different qualities. Each instrument has its own quality of sound on that. So they don't all sound alike. Even between a trumpet and a cornet, you say, well, they pretty much look the same. They pretty much play the same part. But they don't sound the same. They look very similar, but they really don't sound the same. A cornet's usually a little bit mellower. There's a little bit mellower sound on that. So questions. So we need to make some rules so we can use some problems. Now what's nice is strings and two open and tubes have the same rules. They have the same rules. Now the first thing remember, n is the harmonic number. N is our symbol for harmonic number. And n is greater than or equal to 1, and they are integers. These are integers greater than or equal to 1. Harmonic numbers are integers. So first of all, if I want the nth harmonic, and the nth could be the 10th harmonic, the 20th harmonic, and so on, is going to equal n times the fundamental. That's the frequency. Twice the frequency, 3 times the frequency, 10 times the frequency, 100 times the frequency, and so on. L is equal to the harmonic number over 2 times the wavelength. Lambda is equal to 2 over the harmonic number times the length. So you can tell that. Now, just because I know the wavelength, does that mean I know what the frequency is? No. It's just telling me about wavelength, because there's other factors that affect frequency and things like that. The big one, what do you think is the big factor for what frequency an instrument actually plays? Well, how do we relate wavelength and frequency? What value what's something that includes wavelength and frequency? V word.
Velocity.
What? Velocity. The velocity of sound. But the velocity of a wave, that's how they'd be related. So is speed of sound same all the time? We treat it as a constant, but when the temperature goes up, changes, temperature goes down. Anyone who's a musician knows that when you play on a cold day, your instrument's going to go what? It's going to go higher. Yeah, it's going to go sharp. It's going to go sharp. You got to make your instrument longer. You got to pull out. On a really hot day, it's going to go flat. You got to push it in. You got to push it out. However, you have to tune. Different instruments tune different way. Like saxophones, you have corks on the end of the neck, and you bring the mouthpiece in and out on that. You know, trumpets and trombones, they have little slides they pull in and out and things like that. Even on trumpet, they play with valves. They actually have a slide that they can use to actually alter the frequency while they're playing. That's really what, if you look at a trumpet, there's like a ring, like for a finger ring on there. It's actually attached to a slide, and they can slide it in and out as they're playing to adjust it. For woodwind players, we actually have to use our lips. Either you clamp down the reed or you loosen up on the reed to actually change the frequency as you're playing. Because you don't, just because you're in tune at one frequency doesn't mean you're in tune at all frequencies. You know, oxymoron, in tune saxophone. It's an oxymoron. On that. It's like trumpet players being able to told to play louder. You know, it's happened so rarely they'll write down the calendar, was told to play louder today. Same with saxophone players. I got told to play louder in our concert, next concert I got to play. She said, but not too loud. And I wrote that down, not too loud. It's actually it's a solo piece, which is why she wants me to play louder. Now, so this is strings. For our one closed, one open tube, rules are a little different.